Okay, so this is gonna be Chem 118C Week 1, Summer Session 1, 2025 for Lievens. So talking about chapters 19 and 20. Chapter 19 is about carboxylic acids, and then chapter 20 is gonna be about carboxylic acid derivatives. So carboxylic acid is going to be a functional group where we have a carbonyl right next to an OH group. So that is a carboxylic acid right there. So the first thing that Lievens went over is the industrial methods on how to create or how to synthesize carboxylic acids. And this is more of a note card thing where I would recommend you guys drawing these out on the note card because the mechanism is not tested. It's more of a memorization thing where you see every single reaction here creates a carboxylic acid, right? And you might have to know the name of it because just in case it shows up in vocab. So the first one here, we have basic conditions, sodium hydroxide, right, NaOH plus carbon monoxide, CO, at 100 psi pressure, 150 degrees Celsius, creating this carboxylate ion where we have a negative charge on that oxygen right there with a sodium ion, and they are going to ionically bond to each other. And then we could do acid workup with H3O plus to protonate this carboxylate ion into this carboxylic acid right here, right? And the reason why we get a carboxylate here in the first reaction is because we are in basic conditions with the NaOH right there. And in basic conditions, we are going to get the carboxylate. We cannot get the neutral carboxylic acids because the OH minus in basic conditions here, which we have in excess, is just going to deprotonate that carboxylic acid, getting this carboxylate ion right here, which is why we need a second step of acid workup like H3O plus or H2SO4 to protonate this carboxylate ion into this carboxylic acid right there, right? So this is more of a note card mechanism in reaction right here, right? And same as for this one, we have methanol, CH3OH plus carbon monoxide with these reagents and conditions, which would create this acetic acid, right? And the name of this reaction is Monsanto process. Okay, the next one is going to have 1, 2, 3, 4 carbons, butane, reacting with these conditions and reagents, creating 2 acetic acids right here. So that's the third industrial reaction that you need to know. Okay, and in laboratory scale, we could produce a mass amount of carboxylic acids when researchers need it. And that's just a conceptual thing right there, right? Now, the next thing we're going to go over is oxidation from alcohol or aldehydes. So right here, we have a primary alcohol where we have this OH here attached to a carbon that's attached to one other carbon, right? When we oxidize it using a strong oxidizing agent like Jones reagent, we're going to get a carboxylic acid, right? But it's first going to go through the aldehyde intermediate, and then it would be further oxidized stronger into a carboxylic acid using any of these strong oxidizing agents, right? These are the Jones reagents that are acidic. This is the basic KMNO4 plus NaOH, basic strong oxidizing agent. And this is another acidic oxidizing agent, HNO3, right? And you're going to see more of this at the end of 118C. Okay. Now, the next thing that carboxylic acids can do is like another way that we could form carboxylic acids is going to be through an organometallic reagent, like a Grignard reagent or an organolithium reagent, right? So recall from 118A, this is the organometallic reagent or Grignard reagent right here, where the carbon directly attached to the MGBr is partial negatively charged. That's the nucleophile right there. This carbon of the CO2 is electrophilic. It has a partial positive charge because it's attached to 2 electronegative oxygen atoms right there, right? So we have our electrophile here, our nucleophile right here, which is the negative charge carbon directly attached to the MGBr, and then the electrophile right here, which is positively charged, where this is gonna attack this carbon right here, push the double bond onto the oxygen because we're creating a new bond between this carbon and this carbon right here, and we would have to push this bond onto the oxygen to conserve the octet rule, right? Which is going to give us this right here. So I could make it more clear by starring and dotting the nucleophile and electrophile. So this is the nucleophile right here, which is the starred atom because it's directly attached to the MGBr. This is the electrophile right here because it is positively charged, right? And we could draw the mechanism by having this star or the nucleophile attack the dot, creating a new bond between the star and dot. But this carbon here is going to have 5 bonds if we don't do anything else. So that's why we would have to also pop this double bond onto the oxygen, which creates this O minus right here, where this is the starred carbon right here. This is the dot carbon right there. And then this right here is the new bond that we formed between the star and dot carbon, right? This carbonyl here is going to be this carbonyl right here that is untouched, but this O minus here came from this carbonyl like double bond popping onto the oxygen, giving it a pair of electrons and making it negatively charged. Then we could use H3O plus acid workup to protonate the carboxylate ion into this neutral carboxylic acid right there, right? So that's another way to form carboxylic acids. And notice how here in this specific reaction, the organometallic reagent, we increased the molecule's carbon count by 1, right? Because before we see that there are 1, 2, 3, 4 carbons, right? But we increased it by 1 carbon, which is going to have it 1, 2, 3, 4, 5 carbons like that, right? And that's through the organometallic reagent like that. Okay, so that's good for synthesis right there. This is a synthetic route where you can create an organometallic or Grignard reagent from this halocane through Mg, and then we could then have this as a starred molecule, which is the starred molecule here, and this is the dot carbon, which is that dot carbon right there, and this came from the CO2 right there, and this is the acid workup right there. Yeah, this recording will be posted later tonight or tomorrow morning, but it will be posted, and I'll post it to the Discord, the big Discord server. Right? Any questions on this? Yep. Okay. So another thing here is going to be this organolithium right here, where the starred carbon or the nucleophile is that C directly attached to the lithium. That's the nucleophile. This C right here is the dot, which is the electrophile. This is the star, this is the dot. This is the neo bond between the star and dot right there. And then this right here came from the CO2, right? Think of this Li as the MGBr. It will just dissolve away in the solution, right? And we also increased the molecule's carbon count by 1, because we see here that in the reactant side, we have 1 carbon. In the product, we have 2 carbons. This extra carbon here that was not there before came from the carbon of the CO2, the carbon dioxide right there, right? Okay, any questions on this before we move on to hydrolysis of nitrile, the other method to form carboxylic acid?
Could I see the previous reactions that you went over?
Yeah, so we went over industrial methods to create carboxylic acids, which are these 3 reactions right here. The mechanism will not be tested on the midterm or final, right? But I recommend you drawing these reactions down in your note card, because it can be tested as predicted product, right? So you just have to recognize the reactant, reagent, and then the products here would be these carboxylic acids right here. Okay, and then we went over oxidation of primary alcohols with strong oxidizing agents, like the Jones reagent here, and then the K-4 with NaOH and HNO3. Those are just the strong oxidizing agents that you need to recognize that reacts with the primary alcohol to create a carboxylic acid right there. And then we just went over the organometallic route, which increases the molecule's carbon count by 1, right? And that extra carbon comes from the carbon dioxide, the CO2. Okay. Yeah. So the next one here is also going to increase the molecule's carbon count by 1, and that's going to be the hydrolysis of nitrile. So this right here is the CN, right? Where I'm going to just color code this carbon here of the CN as a red dot, which is this red dot right here. This entire nitrile group, the C triple bond N, is this carboxylic acid right here. And the reagents that would convert this nitrile into that carboxylic acid is going to be acid, water, and heat, or base, water, and heat, right? The reason why we need a second step of H3O plus is because if we did not do a second step of H3O plus and we just did NaOH, water, and heat in basic conditions with no acid workup, we would get this carboxylate ion here because we're in basic conditions, right? Even if this became a carboxylic acid, the basic conditions hydroxide ion is just going to deprotonate the acidic proton from the carboxylic acid, leading to this carboxylate ion right here, which is why once we have that carboxylate ion, we could do an acid workup step, which is the second step here, to protonate the O minus into this carboxylic acid right there, right? So where can we get the nitrile? There's two ways that you learned how to do that. The first way is going to be through SN2 reaction from 118A, right? Let's say we have this secondary haloalkane, right? Because this carbon here is attached to a halogen, a good leaving group, bromine. And this is a secondary haloalkane because that carbon there directly attached to the leaving group is attached to two other carbons, making it a secondary haloalkane. And we have a weak base, strong nucleophile here, the cyanide ion, Cn minus, and this is a big indicator of an SN2 reaction. And back in 118A, when we learned about SN2 reactions, they do a backside attack and invert the stereochemistry, right? So this Cn minus here is the nucleophile. This carbon here directly attached to this electronegative good leaving group is the electrophile because it's partial positively charged. So this nucleophile here is going to attack this electrophilic carbon, kick out the leaving group, and invert the stereochemistry, right? Because we're gonna have the wedge be converted to a dash. The Br minus is now floating around in the solution. This is the nitrile that we use to attack that electrophile right there. And then we could do hydrolysis with acidic conditions, water, acid, and heat to convert this entire nitrile into this carboxylic acid right there, right? And we see here the molecule has one extra carbon. This is the extra carbon right here. And that extra carbon came from this nitrile, like that, okay? Okay, so another way to create that nitrile is through nucleophilic acyl addition to create the cyanohydrin. So if you have an aldehyde or ketone, right, and you have a Cn minus, this Cn minus can attack this electrophilic carbonyl carbon, creating a new bond between this carbon and that carbon. But that's going to break the octet rule for this carbon right here, right? Because that carbon already has 4 bonds, 1, 2, 3, 4. If it creates a new bond with that nitrile right there, we have to pop this double bond onto the oxygen to conserve the octet rule. So 2 electrons from this bond are going to go onto that oxygen, giving this oxygen a negative charge, right? And then this negative charge here can become an alcohol through the acid workup, like H+ catalyst right there. And this right here is what we call a cyanohydrin when we have a cyanide and hydroxyl group on the same carbon, creating a cyanohydrin, right? And then we could do hydrolysis of nitrile. And in this case, she did basic conditions where we convert the nitrile into the carboxylic acid right there. Okay. Any questions on this reaction before we move on to the next one? Okay, so chapter 19 and 20, they follow a very general pattern, right? They follow a main mechanism, which is nucleophilic acyl substitution, NAS, right? Where we have a carbonyl right here with a leaving group attached to that carbonyl. And this carbonyl here is electrophilic because it's partial positively charged since it's attached to an electronegative oxygen atom. And then we could use a nucleophile to attack that carbonyl carbon, push the double bond onto oxygen, creating an O-, right? Which can be protonated to become the OH to give us this tetrahedral intermediate right here, where this is the new bond that's formed between the nucleophile and carbonyl carbon. This used to be a double bond, right? This H here came from the acid workup step, but this is a tetrahedral intermediate because this carbon here is very unstable, right? It's attached to a lot of electronegative atoms, like this oxygen here, this nucleophile here, and this leaving group right here. And we changed the hybridization of this carbonyl carbon. Before it was sp2 hybridized, but it became sp3 hybridized when we gave it the new bond to the nucleophile right there. Then we could do elimination by getting rid of this leaving group, right? And we could do that by reforming the carbonyl and kicking out that leaving group, right? Where this hydrogen right here, this oxygen right here is still attached to this hydrogen, right? And because this oxygen has 3 bonds, it's positively charged, but some base, right, in the mechanism can come around and deprotonate that carbonyl oxygen to make it neutral, which is this neutral product right here, right? So what you're basically doing here is substituting the nucleophile with the leaving group, right? We see that in the reactant, we had a leaving group next to the carbonyl, but in the product, we have a nucleophile next to the carbonyl now, right? Okay. And this can happen in 2 conditions. It can happen in basic conditions or in acidic conditions. Our we supposed to know the mechanism for nucleophilic acyl substitution? Yes, you are, but this right here is too generic, so don't worry about this one, right? This is just like the big idea overview of what's about to come next, right? Because nucleophilic acyl substitution can either happen in basic conditions, which is the shorter mechanism, or it can happen in acidic conditions, which is the longer mechanism, right? And I'm gonna show it to you step by step by actually just drawing it out. So let's start with the shorter one first. Basic conditions. Okay, so nucleophilic acyl substitution in basic conditions. Okay, so the reactant here is gonna have a carbonyl attached to some leaving group. And the reagents that we're gonna have in basic conditions here is that the nucleophile is gonna be negatively charged, right? With a solvent that is neutral, okay? So for example, it could be like OR minus, and then the solvent can be ROH minus, the neutral version of it, okay? There's many other ones, like it could be an amine where the solvent is ammonia, right? Or it could be hydroxide where the solvent is water. Basically, the solvent here is just the nucleophile negative charge with an extra hydrogen, extra proton right there, right? But we're gonna go over that when we go to those set of reactions. This is just like the big idea right here. This negatively charged nucleophile here is a strong nucleophile. It's strong enough to attack this electrophilic carbonyl-carbon right there. And because we're gonna make a new bond between this carbonyl-carbon and nucleophile, we have to push the double bond onto the oxygen to conserve the octet row, right? And when we do that, we're gonna get this tetrahedral intermediate right here, where the double bond oxygen becomes a single bond O minus. The leaving group is still there. This right here that I just drew out is a new bond. That right there is the new bond between this carbon and this nucleophile right here. And this is what we call the tetrahedral intermediate, right? That should be in the vocab, like as circle an option or write it down. This is the tetrahedral intermediate. Now, once I have this tetrahedral intermediate, we can reform the carbonyl, right? The carbon double bond oxygen, but this carbon is going to break the octet row if we don't do anything else, right? It's going to have 1, 2, 3, 4, 5 bonds. To conserve the octet row, we have to kick something out. If we were to kick out the nucleophile, we go backward, right? We're going to get the same thing here. But if we kick out the leaving group, we're going to get the new product where we substituted the leaving group with whatever nucleophile we had, like that. And you can think of this as in 2 steps: addition, elimination. The first step, we did addition, where we added the nucleophile to the carbonyl. And then the second step, we did elimination, where we eliminated the leaving group, like that. So basic conditions of nucleophilic acyl substitution is very fast. 2 steps: addition, elimination, right? Any questions on that before we move on to the acidic conditions? Okay, let's move on to acidic conditions now, which is the longer one, right? And that's gonna be probably the more common one that's just gonna test you on the exam. So, nucleophilic acyl substitution in acidic conditions. Okay, and I'm gonna show you guys like the conceptual stuff behind it as well, so then you guys can understand it and answer vocab questions if it shows up, if you test you conceptually, like Helix does for conceptual multiple choice questions. Since this is all reversible, do we have to know the mechanism for reverse? Yeah, this right here is right, because the leaving group here can attack that carbonyl, push the double onto the oxygen to create this tetrahedral intermediate. And then when you reform the carbonyl, you can kick out the nucleophile to get back to this reactant right there, like that. Right? So the mechanism is still the same. Okay. Now, let's say we have a carbonyl with the leaving group. And this time we are in acidic conditions. So in acidic conditions, right, we're gonna have a neutral nucleophile. There's no negative charge in acidic conditions. It's either gonna be neutral or positively charged with some sort of acid. And the most common organic acid that you're gonna see for these reactions is sulfuric acid, H2SO4. Okay, so this nucleophile with the proton could be water, it could be alcohol, or it could be an amine, or it could be a carboxylic acid, right? There's a lot of them, which we'll go over. But this is just a big idea for now. And we have a proton source, acidic conditions, H2SO4. Now, this nucleophile here that is neutral, no negative charge, is not as a strong nucleophile as this nucleophile here with the full negative charge, right? Because it's neutral. And because of that, without acid, this nucleophile here is not able to attack that carbonyl-carbon because it's not strong enough. Right? So this right here would be no reaction if we had no acid. If we just have a weak neutral nucleophile and a carbonyl right here, no reaction. For most cases, right? I'm going to show you guys the example where there is a reaction because it depends on what leaving group this is, right? For most cases, there will be no reaction, but depending on the leaving group, there could be a reaction. Okay, so what we have to do next is see this carbonyl oxygen here is going to be the base. That's going to get protonated by the acidic conditions we have, H2SO4. Okay, and because this is reversible, I'm going to draw reversible arrows here, where this carbonyl oxygen right here gained a proton from the acid. And because this carbonyl oxygen has 3 bonds, it is going to be positively charged. Its formal charge is positively charged, right? Now, this carbonyl carbon here was electrophilic, right? But now, because we protonated the carbonyl oxygen, it's now a bigger electrophile. It has a bigger positive charge now. It's a very strong electrophile, right? Because this oxygen here that's positively charged is very angry. It does not like that positive charge at all. So what it's going to try to do is that it's going to try to pull electrons from that carbon right here to become neutral again, right? And because it's pulling electrons from this carbon right here, it's taking away its negative charge. And because it's losing negative charge, it's going to become a bigger positive charge right there. So this is the activation step, where we activate the electrophile to become strong enough for this weak nucleophile to then be able to attack that carbonyl carbon and pop the double bond onto oxygen to create this tetrahedral intermediate here. Right? And because we're giving this oxygen a pair of electrons, this oxygen here is now going to be neutral. We're going to neutralize that positively charged oxygen. This right here that I just drew out is the new bond between that carbon and nucleophile right here. Okay? And because the nucleophile here gained a bond, it's going to be positively charged. Now, this is where the proton transfer steps happen, right? We want to be able to keep this new group that we just added to get the new product. But right now, it's a good leaving group. That's bad. We want to kick out this old leaving group, but right now, it's a bad leaving group. So in order to make this into a bad leaving group, we're going to deprotonate the nucleophile to make it neutral. And make that into a bad leaving group, which is good. Now, we want this leaving group to be a good leaving group. So to do that, we can protonate it with the reformed acid catalyst that we just did in the last step to get this protonated leaving group right here. Okay, now from here, once we have this good leaving group, we could reform the carbonyl, kick out that leaving group, which leaves as a neutral molecule. And if we get our last last intermediate right here, the last part of this mechanism is to neutralize the positively charged oxygen by deprotonating it with the conjugate base of H2SO4 to reform the acid catalyst, H2SO4, right? We are going to reform this H2SO4 right here. And we did the same thing as the last mechanism in basic conditions, we substituted the leaving group with whatever nucleophile we used in the reagent. But in acidic conditions, it's way longer. It's more longer than 2 steps for sure. Right? An acronym that Maria Jones uses that can help you with this mechanism is peptide. Right? In acidic conditions, where the first step is protonation, where we protonated the carbonyl oxygen, and then we did addition, where we added the nucleophile, and then these next 2 steps here are the proton transfer steps, right? Where we deprotonate the group you want to keep to make into a bad leaving group. And then you're going to protonate the group you want to kick out. Okay, and then once we do that proton transfer step and we get the desired tetrahedral intermediate, we do elimination, where we reform the carbonyl and kick out the good leaving group. And then the very last step is deprotonation. So I'm going to walk you guys through that again. For peptide and acidic conditions, protonation. Protonate the carbonyl oxygen to activate the carbonyl. Once the carbonyl is activated, we do addition of the nucleophile to create this tetrahedral intermediate. Then we do the proton transfer steps, where we deprotonate the group we want to keep, which is this new group right here. We want to keep that group, so we deprotonate it to make it into a bad leaving group. And then we protonate the group we want to kick out, which is this group right here. This is a bad leaving group, which is going to become a good leaving group by protonating it. Now, once we have this desired intermediate, we do elimination by reforming the carbonyl and kicking out this leaving group here, right? And then the very last step of the mechanism is to deprotonate this positively charged carbonyl oxygen to create this neutral carbonyl right there. So that's an acronym you could use if you don't want to draw this mechanism on your note card, right? So that's gonna be like 1, 2, 3, 4, 5, 6 steps in acidic conditions. Any questions on that before we move on? For acidic conditions? Okay, so let me just make sure that's what Lievens also did. Basic conditions, addition, right? Nucleophile attacks carbonyl, push the bonds of the oxygen, get that tetrahedral intermediate, and then elimination. Reform the carbonyl, kick out that leaving group, get the final answer. Now in acidic conditions, we protonate the carbonyl oxygen to activate the carbonyl carbon, make it a stronger electrophile. In order for the weak nucleophile to attack, pop the bonds of oxygen to create this tetrahedral intermediate. And then what she did here is that she did the proton transfer steps in the same step, which is faster, right? You can do that on the exam and you still get full credit. This leaving group here is gonna get protonated the same time as this nucleophile gets deprotonated, right? Because this leaving group here is grabbing that proton of the nucleophile. So we could get straight to here in one step, right? And then once we have this good leaving group, we could reform the carbonyl, kick out the leaving group to create this positively charged carbonyl, where we could then deprotonate to get this final answer with the nucleophile right there. And these are the side products, which you do have to draw the side products for mechanism, right? For predicted product, you would have to draw the organic products, which are anything with carbons and hydrogens. Right? Any questions on that before we move on?
For the side products, do you need to write it like every step, like what side products you formed in the previous steps?
For mechanism with the boxes, yes, you do for Lievens class, unfortunately.
Okay, thank you.
Yeah. Yeah. Who did you have for 118B?
I had Ida for 118B and I had Wei for 118A, so I don't think.
Oh, yeah, it's different. Yeah, they're different. Right. But Lievens, the way that she does her mechanism problems is that she wants you to draw out the side products throughout the whole mechanism, and she does give you boxes for the mechanism problem, so that's good.
Thank you.
Okay, so this next section here is going to talk about carboxylic acid derivatives already, but let me show you guys what they are first. So a carboxylic acid is a carbonyl next to an OH. A carboxylic acid derivative is going to be I'm just gonna draw it out and explain it later. Okay, so the carboxylic acid leaving group is an OH. The carboxylic acid derivative is gonna have a carbonyl, but the leaving group, the LG, is different. It's not gonna be OH, right? It could be a halogen, where X can be like chlorine or bromine. It could be a carboxylate. It could be an OR. It could be an amine, right? So these are the main carboxylic acid derivatives. This nitrile right here is a cousin, right? It's still considered a carboxylic acid, but derivative, but it's a cousin because it has no carbonyl, no carbon double bond oxygen. Right? When you have a halogen as the leaving group, we call that an acyl halide. When you have a carboxylate as the leaving group, we call that an anhydride. When you have an OR as the leaving group, we call that an ester. When you have an amine as the leaving group, we call that an amide. Right, and this right here is a nitrile. No carbonyl though. Nitrile. Right. All of these derivatives can be hydrolyzed into the carboxylic acid through a reaction called hydrolysis. Right? So the acyl halide, the anhydride, the ester, the amide, and the nitrile can be converted back to the parent functional group, carboxylic acid, through hydrolysis. Right? So let's look at the specific cases.
I have a question.
Yeah.
I think she also went over like the cyclic names like lactams and stuff. Could you like go over those as well? Because I got kind of confused.
Yeah. Lactam, lactone. So let's go over that. So a lactone is a cyclic ester, right? So first, let me go over some examples of regular esters with you before we go over cyclic ester. So an ester, an example of that would be this carbonyl with that OR group right there. Right. It could also be something like this, where there's oxygen, like that. Or it could even be something like this, right there, right? Where we have a carbonyl next to, oh shit, that's a cyclic one. Next to an OR group, like that, right? A cyclic ester is gonna be when we have the same thing, but the ester is cyclic now, right? Like the carbonyl carbon and OR group of the ester are in a ring. So that's one example. Another example would be something like this, right? Where it could be like a 6-membered ring, which is this, or it could be a 5-membered ring, which is that. But these are considered cyclic esters, and a fancy name of a cyclic ester is just a lactone. A lactam is a cyclic amide. So a regular amide would have a carbonyl next to like an amine, like that, or like that, or like this, right? But a cyclic amide, or a fancy name for the cyclic amide is a lactam, is going to have a cyclic structure to the amide, like that. It could be a 6-membered ring, like I just drew, or it could be a 5-membered ring, like that. Right? Now, the nomenclature could be tough for lactam and lactone, but there is a document for nomenclature, for Lievens especially, right here, where we can search it up and see her process on naming those. Where we can search it up through find and replace. Let's do lactam. Search. Right. So this is the nomenclature for this is 119C. 118C, lactam. Mhm.
I think because she said like she wasn't testing heterocycle nomenclature, but I think that like in the Discord someone sent a picture of a heterocycle nomenclature.
Oh yeah, with the lactam or lactone, something like that.
Yeah, but I thought like she said we weren't learning that part until later, so I just like don't know.
Yeah. When is that homework due?
On Thursday.
Thursday. Okay, okay. Shoot. And she said she wasn't gonna go over the nomenclature of those.
Yeah, she only like introduced it, but like in class she even like wrote it in grade like she even wrote it like that's for like lactams and lactones are for like later, but I
Mm,
think it's still in our homework anyways.
in the homework anyway. Yeah. Yeah. Access. Yeah, yeah, I'm gonna be honest. I don't review nomenclature as much as I do reactions, mechanisms, synthesis, acid base, stuff like that, or spectroscopy. So that's my weakness right now. The nomenclature stuff. I'm not too sure on that. Sorry.
Thank you.
Uh-huh. But we could look at this example right here. Um, and see how we could think about this. This structure right here. This is an oxa cyclohexane. We put the oxa there because there's an oxygen in the ring. This is a lactone. And then the cyclo is the ring part. Hexane is the six-membered ring part. Right. The oxygen in the ring is position 1. And then the carbonyl gets priority next. Yep. So that's gonna be 2. So the direction is gonna be counterclockwise. 1, 2, 3, 4, 5, 6. And then at carbon 2, we put the one there to show the ketone. At carbon 4, that's where the alkene starts from 1,1B nomenclature, the alkene nomenclature. And then carbon 6, there's the methyl there. And then you could do R and S for that carbon 6. And because this alkene is Z, so we do 4Z, 6S, 6-methyl, oxycyclohex dash 4-ene because there's an alkene there, starting at carbon 4, and then 2-one. So that's the lactone example. Let me try to find a lactam example. Lactam. Yeah. Yeah, I don't think there's a lactam example in here. Yeah, but hopefully someone asked her about that in like piazza or like lecture or office hours, that problem.
Yep, thank you.
Yep. Okay. So going back to this right here. We have an acetyl halide because this leaving group here is a halogen, Cl. And this is the most reactive derivative. Right? Because actually, I have to go over that with you guys as well, so then it makes more sense of why that's the most reactive derivative. I'm gonna draw out the carboxylic acid derivatives in this order right here. So X and the anhydride, and then the carboxylic acid itself, the parent one, and the ester, and then the amide, and then the nitrile. Okay, so I drew in this specific order because reactivity will increase from right to left. Right, where the acyl halide is the most reactive, the nitrile is the least reactive. Now, there's 2 factors on why this is the case. The first factor is going to be about leaving group ability. So I'm going to circle all the leaving groups of these carboxylic acid derivatives like that. Right, and I'm going to make a dashed line here to show that this is the cousin, because there's no carbonyl there. And then I'm going to draw out the leaving group, leaving with a negative charge. So when X leaves with that negative charge. When this carboxylate leaves, the negative charge is on the oxygen, negative charge on this oxygen, negative charge on this oxygen, and negative charge on this oxygen right there. Okay. This negative charge here is the most stable on the most electronegative atom, X, like chlorine or bromine. Right, so that's why that's the best leaving group compared to all these other leaving groups right here. Now, when we look at the negative charges on oxygen versus nitrogen, the negative charge on oxygen is more stable than the negative charge on nitrogen. And that's because oxygen is more electronegative than nitrogen is. So that's why oxygen can hold that negative charge better. Right? Now, let's look at why this is a better leaving group than these two here, right? Because these two are going to be relatively similar leaving groups. Right? This negative charge here can do resonance with the carbonyl adjacent to it, next to it. And resonance increases the stability of molecules. So that's why this is a better leaving group. Whereas these negative charge here on these oxygens cannot do resonance. So that's why they are lower than this leaving group here in terms of stability. Right? And then nitrogen is the least because it's the least electronegative atom right there. Okay? The other factor is going to be about the carbonyl carbon electrophilicity, right? Positive charge. The carbonyl carbon of the acyl halide has the biggest partial positive charge, whereas the carbonyl carbon of the amide has the smallest positive charge. And for the acyl halide, there's actually several reasons why, right? Let's say if the X is fluorine, the fluorine is small enough to do resonance with the carbonyl, right? So it can do resonance because the p orbitals can overlap since they're similar size. P orbitals can overlap, but does not want to do resonance. The fluorine does not want to do resonance because it's the most electronegative atom. It's like it wants to keep its electrons, right? Because of electronegativity. Since fluorine is the most electronegative atom, it wants to keep its pairs of electrons. It doesn't want to donate its electrons to this carbonyl right here. And because it's not donating electrons to that carbonyl, it's not gaining negative charge. And because it's not gaining negative charge, it remains a big positive charge. Whereas if you look at the nitrogen case, nitrogen, since it's less electronegative than oxygen and halogen, it's more willing to donate electrons to the carbonyl. And because it's donating electrons to the carbonyl, this carbonyl is gaining more negative charge, reducing the positive charge character. Right? Now, if X is chlorine, bromine, or iodine, they're not as electronegative than fluorine, so they're more willing to give up electrons, but cannot do resonance because of the atom size, because the p orbitals do not overlap. They're bigger atoms, like chlorine, bromine, iodine, they're bigger than carbon is, so the p orbitals do not overlap well, so resonance does not happen well with them. Do not overlap well. Okay. The positive charges on these ones with the oxygens here are going to be relatively similar. Right. Smaller than the acyl halide, but bigger than the amide, because the amide here, the nitrogen, is donating more electrons to the carbonyl right there. Okay. So the electrophilicity of the carbonyl carbon is not as a big factor as the leaving group ability. The leaving group ability is a bigger factor here. Okay. Now, here's an important distinction. I'm going to make a line here to show that these two carboxylic acid derivatives, the acyl halide and the anhydride, they are the top two most reactive derivatives. Right? The acyl halide and anhydride, they're super reactive. They do not need an acid catalyst or a basic catalyst or heat. Right? Whereas these lower, less reactive derivatives here will need acid catalyst or base catalyst or heat to make the reaction go through. So let's look at some examples of that. And it's going to be more clear with a chart and table, but that's better if after we learn all the reactions individually. Right? So if we go back to this right here, we see that this is an acyl halide, where if we just put water, there will be a reaction. Right? It's going to do hydrolysis, where we're going to convert this acyl halide to this carboxylic acid right here in a few seconds. And HCl is going to be the side product. If we use anhydride, we could just use water as well without any acid or base catalyst. But it's going to take a few minutes to hours because it's less reactive than the acyl halide to create the carboxylic acid here. Right? We're basically substituting that leaving group with the OH right there from the water. Okay? Because this is symmetrical, we get two of them, right? Because this can be the LG, the leaving group, right? Or this can be the LG, the leaving group, creating that right there. Okay. Now, if you use an ester, you're going to use water with some sort of acid or base catalyst. Right? You could be acid or base catalyst. If you use an acid catalyst, you're going to get the neutral carboxylic acid with this alcohol as the leaving group right there. But if you use base and just base, no acid workup, right? Like let's say NaOH with water, you're going to get the deprotonated version of the carboxylic acid, the carboxylate right there. But when you have a second step of acid workup, like H3O+, you can protonate the negative charge carboxylate into this carboxylic acid right there, like that. Okay. Now, if we go onto the amide, the least reactive derivative, we're going to need water, acid, or base catalyst with heat, right? Heat is needed here. We need to add more energy because it's the least reactive derivative, and it takes the longest to convert like that leaving group to the OH right there, and this is the leaving group right there to create that amine. Okay, so all of these are hydrolysis reactions. These are hydrolysis reactions. Some require catalyst, some do not require catalyst. And that's because of this concept here, the reactivity of the carboxylic acid derivatives. Okay. Okay. Okay, so now the next thing is going to be reactions of carboxylic acids. So carboxylic acids are not great at nucleophilic acyl substitutions, like the one that we just went over in acidic conditions and basic conditions, right? Where this is the basic conditions, the nucleophile attacks the carbonyl-carbon, or acidic conditions, right? The same thing, nucleophile attacks the carbonyl-carbon. The common thing between those two conditions, acidic and basic conditions, is that the nucleophile always attacks the carbonyl-carbon, right? But the carboxylic acid itself, the parent function, is not great at that mechanism. The reason why is because if you use a basic nucleophile like OR minus, this OR minus here is not going to attack the carbonyl-carbon like we are used to seeing in the basic conditions nucleophilic acyl substitution. What it's going to do is that it's going to deprotonate the carboxylic acid. So nucleophilic acyl substitution will be good for acyl halides, anhydrides, esters, and amides, right? Like in acidic and basic conditions, those functional groups besides the carboxylic acids will be used for NAS, yeah, the derivatives of carboxylic acid. But the carboxylic acid itself is not very great at nucleophilic acyl substitution in basic conditions, right? That's the most important thing. In basic conditions, Because in acidic conditions, they can do nucleophilic acid substitution. In acidic conditions, it's all good. Right? It could do nucleophilic acid substitution in acidic conditions. The reason why it cannot do it in basic conditions is because of this acidic proton. So if you put any kind of strong base in the solution, that strong base is going to look for the most acidic proton, which is this carboxylic acid right there, and deprotonate it to get that carboxylate right there. Right? But if you use a non-nucleophilic nucleophile like CO minus, when CO minus attacks that carbonyl right there, right? This CO minus is not a very strong base because the negative charge on this Cl right here is very stable, right? Because chlorine is very electronegative, stabilizing the negative charge very well. And because it's stable, it's not as basic, right? It doesn't want to grab the proton as much. But what it can do is that it can act as a nucleophile because of the full negative charge, attack the carbonyl carbon, push the double bond to oxygen to create this tetrahedral intermediate right here. Right? And then once we get that tetrahedral intermediate, we have two leaving groups, and the better leaving group here is the Cl, the chlorine. So when we reform the carbonyl, we kick out the chlorine, getting back to what we started with. So this is basically no reaction. Okay. Now, this is what we talked about. We can use a poor nucleophile with an acid catalyst to do nucleophilic acid substitution, right? If we have this carboxylic acid here with this alcohol that is neutral, if we don't have acid or heat, no reaction happens. The reason why is because this neutral nucleophile here is stable. It's a weak nucleophile. It cannot attack this carbonyl carbon by itself. Right? Think of it like this. A weak nucleophile cannot react with the weak electrophile. Someone has to be strong for the reaction to occur, right? So the nucleophile can be strong. So if this is O or minus, then it can just attack it by itself, right? But it's not. It doesn't have a full negative charge. So the nucleophile can be strong, or the electrophile can be strong. Because the nucleophile is not strong here, we can make the electrophile strong by protonating it with the acid we have, H2SO4. Right? And then once it's protonated, this weak nucleophile is now able to attack the carbonyl carbon, push the double bond to the oxygen to create this tetrahedral intermediate. Now, this is going to follow the acidic conditions mechanism for nucleophilic acid substitution. We do the proton transfer step, where we deprotonate the group that we want to keep, which is that nil group right there, and then we protonate the group we want to kick out, which is that group right there. And we could do that at the same time here, right? Kill two birds with one stone there. Now, once we get the desired intermediate, we can reform the carbonyl and eliminate the leaving group. Kick out the leaving group. Now, once we have that, because this oxygen here is still attached to that hydrogen, this oxygen is positively charged, where the last step is to deprotonate and neutralize that positively charged oxygen using HSO4 minus and reforming the acid catalyst, H2SO4, to create that final product right there. Right? And the name of this reaction is Fischer esterification. And the three ingredients for Fischer esterification are going to be carboxylic acid, alcohol, and acidic conditions. This can never work in basic conditions. Never work in basic conditions, right? And that can show up on the test too, because Lievens could trick you like that, right? And let me show you an example. So let's say we have this carboxylic acid right here, and then we have this alkoxide ion, ethoxide ion, with its solvent, ethanol, right? A lot of people would draw this as the product, where they substitute this OH group to that OR group to get this final product right here, that ester right there. But this is not the answer, right? The reason why is because we have a base here, a very strong base, so we're in basic conditions, which that base is just gonna deprotonate the carboxylic acid to give us this answer right here with no acid workup, that carboxylate ion right there. And this is the answer for that question, which I've seen her test on that before, right? So this green reaction here is just an acid-base reaction, where this is the base and this is the acid, and we just do a deprotonation step to get this final product right there. But people are focused on NAS reaction, nucleophilic acid substitution reaction, where you substitute the LG with the nucleophile, so they forget about this concept here. But if you were given acidic conditions, that would work. Okay. Now, Le Chatelier's principle is important here. this is important for vocab, right? Because all of these reactions here are reversible. The catalyst is acid, right? Because if you increase the amount of alcohol concentration, you're going to go towards the ester side. If you increase the concentration of water, you're going to go towards the carboxylic acid side. Right? So the name of the reaction of this one is Fischer esterification, where we convert a carboxylic acid into an ester with alcohol and acid. Whereas the name of this bottom reaction is hydrolysis, like we talked about earlier, where the reactant here is an ester, which is a derivative reacting with acid and water, going back to the parent functional group carboxylic acid, hydrolysis, right? And the reaction is going to be favored depending on the concentration of alcohol versus water. Okay, now here's the intramolecular example. Let's say we have a carboxylic acid and alcohol, and then acidic conditions. 3 ingredients for Fischer esterification. But because the carboxylic acid and alcohol are in the same molecule, where that means the nucleophile and electrophile are on the same molecule, an intramolecular reaction is going to happen where you're going to form a ring, right, or a cyclic structure. So let's go over the mechanism here. Imagine this is H2SO4. The very first step of the mechanism here of nucleophilic acid substitution in acidic conditions is to protonate the carbonyl oxygen to activate the electrophile. And then the alcohol here attacks the electrophilic carbon right there. And notice how the nucleophile is on the same molecule as the electrophile. This is a big indicator of intramolecular reaction, which is going to form a ring. And what I like to do for all intramolecular reactions where I know we're going to form a ring is I like to number from the nucleophile and go to the electrophile to see how many membered ring we're going to form. And we see that we're going to form a 1, 2, 3, 4, 5, 6 membered ring. And I'm going to highlight that 6 membered ring to keep track of those atoms here. 1, 2, 3, 4, 5, 6. And one atom of the ring is an oxygen atom, right? So we could highlight this portion of the intermediate here, and we could number it the same way that we did in the previous step, where this is going to be 1, 2, 3, 4, 5, 6, right? That's the backbone of the intermediate right there. So that's what you could do to draw out the product and mechanism. Everything else is a decoration, right? Everything else is copy and paste. We see that at atom 1, the oxygen is still attached to this hydrogen right here. So we draw that hydrogen out, and because this oxygen has 3 bonds, it's positively charged. Carbon 2 has a methyl group, which is this methyl group right there. So we just copy and paste that there. Carbon 6 has an OH, which is this OH here. And it used to have a double bond OH, but we popped the double bond onto the oxygen to create another OH right there. And then she didn't complete the mechanism here, but it would be the same as the previous step. Let me actually just finish it out for you guys, so then you guys have this mechanism if this does show up on the test, which there is a high chance that it would. And I'm going to use H2SO4 instead. So let's use the same kind of reactant here. H2SO4. Okay. So NAS in acidic conditions. First step. Protonate carbonyl oxygen. Activate the electrophile. Now, once that's activated, the weak nucleophile attacks the carbonyl carbon, push the double bond to oxygen. And because this is an intramolecular reaction, I'm going to number it from the nucleophile to the electrophile to form a 6-membered ring, where I know one of the atoms of the 6-membered ring here is an oxygen atom. So I could just draw that base template out like this, where this is gonna be 1, this is gonna be 2, 3, 4, 5, 6. Doesn't matter which way you go. Like I did clockwise, but you could have also went counterclockwise. Just make sure you're consistent and copy and paste it correctly. So at carbon 2 methyl group, this oxygen still has a hydrogen and positive charge. Carbon 6 has an OH and another OH. Now redo the proton transfer step from this tetrahedral intermediate now, right? We're gonna kill 2 birds with 1 stone here by deprotonating this group and protonating this group at the same time, right? Because we want to keep this group, so we gotta deprotonate that group. We want to kick out that group, so we gotta protonate that group. And we did that at the same time with those arrows. And then we're gonna get this tetrahedral intermediate right here, where now to kick out that leaving group, we can use the other OH to reform the carbonyl and kick out that leaving group right there to give us this intermediate and water as the leaving group. And then the very last step here is to deprotonate and neutralize the positively charged oxygen to give us our final products right here. Now, as you saw earlier, I was gonna reform the carbonyl from this oxygen and kick out that leaving group, right? But let's see what happens when I did that, right? Let's see what happens when I try to reform the carbonyl from this oxygen and kick out that leaving group. When I do that, this oxygen here will have 3 bonds, 1, 2, 3, and a positive charge. But there's no way to deprotonate and neutralize that positive charge because there's no proton there, right? And this is unstable, so it's just gonna go back to here, which is why we're gonna use the other OH to reform the carbonyl, kick out the OH, because this positively charged oxygen here can be neutralized by being deprotonated because it has a proton right there to give us this cyclic ester or lactone product. Right, so this is an intramolecular Fischer esterification reaction there. Any questions on that? Okay. So now we're going to talk about how to form the carboxylic acid derivatives. The first carboxylic acid derivative that we're going to talk about is an acyl halide, right? Where we have a halogen, like chlorine or bromine, next to the carbonyl right there. And they're hard to form because chlorine and bromine are very good leaving groups. So let's say that we have this carboxylic acid right here reacting with HCl, which is a nucleophilic acid. The first step here is going to protonate the carbonyl oxygen to activate the electrophile and kick out the Cl leaving group to get this intermediate here. Then the Cl minus here is going to attack that carbonyl carbon that's activated, push the double bond to oxygen to get this tetrahedral intermediate there. But when we go to reform the carbonyl and we decide what leaving group to kick out, we're going to kick out the better leaving group, which is the chlorine here compared to this OH. But when we do that, right, we're going to go backwards to what we started with, leading to no reaction. So the trick to create the carboxylic acid is to use SlCO2, which is the structure here, right? So this is going to be carboxylic acid. If you have a carboxylic acid here and you react it with SlCO2 with a base like triethylamine or pyridine, you're going to get the acyl chloride if you want chlorine right there. And these are the side products. If you use PBr3, you're going to get the acyl bromide. Right there. Okay. Mechanism is a no card thing. So I don't have to explain each arrow unless you guys want me to. Right, let me just do it really quickly. So think of it like this. The pairs of electrons on this oxygen of the OH are going to form a carbonyl, a carbon double bond oxygen there. And then one of the double bonds here are going to go into this oxygen, giving that oxygen a negative charge, where that negative charge oxygen is going to attack this electrophilic sulfur atom, push the double bond onto the oxygen, and then this right here is the new bond, right, which comes from this arrow. And then this O minus here is this oxygen right there, because we popped the double bond onto the oxygen right there. And then this double bond here came from this arrow right there, where this oxygen is positively charged because it has 3 bonds. Then this O minus here grabs this proton, and then this bond here goes onto the oxygen to give us this intermediate here. Then one of the pairs of electrons on this oxygen right here is just going to go make a double bond between this oxygen and sulfur, and kick out one of the chlorine leaving groups, which is that right there. And then this right here is going to act as a good leaving group, where this chlorine leaving group that just left is going to come back to attack this carbonyl carbon, push the double bond onto the oxygen, creating that negative charge, but the negative charge is going to grab this proton here and then break this bond and neutralize this oxygen right there to get this intermediate. Then one of the pairs of electrons here are going to go down to form a double bond between that carbon and oxygen. And then this bond here is going to break to create a double bond between oxygen and sulfur to then give us this SO2 product and kick out that leaving group chlorine right there. What the final part of the mechanism is to use the base, like either T or pyridine, in this case it's T, triethylamine, to deprotonate this positively charged carbonyl carbon oxygen and give us our final product there, the acyl halide chloride. Now with PBr3, this oxygen here, pair of electrons, is going to go down to form a carbonyl, and then this carbon oxygen here is going to attack the phosphorus, where this yellow oxygen is that yellow oxygen, this blue oxygen is now this blue oxygen, right? Because we reformed the carbonyl, that's that carbonyl right there. She just rotated this bond right there. This yellow oxygen is now attached to this phosphorus. We kicked out that bromine, so that's why there's only 2 bromines on that phosphorus. This is considered the leaving group now, where the Br minus that got kicked out earlier is going to be the nucleophile to attack this carbonyl carbon and then kick out that entire leaving group, which is this right here, right? But then when we kick it out, right, this oxygen here is going to have a negative charge, which that negative charge leaving group is going to deprotonate this positive charge oxygen to get to this neutral version right there, right? But she didn't draw that out. If you were to draw it out, it would look like this, right? When we kick out the leaving group, this oxygen will have a negative charge, which can then deprotonate that carbon oxygen to get this and that right there. Okay. And then we're going to get 3 of these because this can like actually happen again because we have 2 more bromines right here, right? This was the first time because we have 3 bromines of the PBr3. The first one forms this, but because we have 2 more bromines, we could do it 2 more times to get 3 of these.
Predict the product. Should we write that we get 3 products?
No, you don't have to. For predicted product, you could just write that as the answer. You don't have to write times 3. Yeah. This is more useful for synthesis problems. Like if you're trying to create the most reactive derivative, and that can do like a lot of the reactions, most of the reactions from a carboxylic acid, you could either use PBr3 or SlCO2. I've seen this mostly on predicted product problems. I mean, and synthesis problems. Yeah.
Thank you.
But yeah. Okay. So you can form anhydrides with the loss of water. So let's say we have two carboxylic acids here. With heat, we could form this anhydride with water, but that's going to be a very low yield, right? Because carboxylic acid is a bad nucleophile, right? So think of this right here as the Lg being substituted with that nucleophile right there. It's basically saying that the second equivalent of it is trying to attack this carbonyl, push the double bond oxygen, but this is very weak. And the reason why this is a weak nucleophile is because this oxygen here with the pair of electrons can do resonance with the carbonyl right there. And because it could do resonance, that increases the stability of the structure. And because it's more stable, it's less reactive. And because it's less reactive, it's a weaker nucleophile. So that's why it's going to be in poor yield. Intramolecular reactions work well because we're going to produce water, create more craziness, randomness in the solution, in the surrounding environment, which is a good thing, right? Because we start with one particle and then we get two particles. So this reaction here, intramolecular reaction, is faster than this intermolecular reaction, right? Where the nucleophile and the electrophile are on the separate molecules. Okay. And then the water here comes from this OH and H right there, right? H2O. And then this pink oxygen right there is that pink oxygen right there, where we just fuse them together like that to create this cyclic anhydride, right? It's a cyclic anhydride because it's fused in a cycle, in a ring like that. Okay, and here's the mechanism, which is a cyclic mechanism. And think of it like this, right? This carbonyl oxygen here is attracted to this partial positive hydrogen through hydrogen bonding. So this carbonyl oxygen here is going to attack that hydrogen using one of its double bonds. And then the bond between this hydrogen and oxygen is going to create a double bond right here. And then this oxygen here is going to gain a negative charge, which is going to attack this carbon right there, which is this right here. So if I highlight things, like let's say this is that, that's that. This red hydrogen is that red hydrogen. This green oxygen is that green oxygen. This blue oxygen is this blue oxygen. And then this carbon here is yellow right there, right? And then we made that new bond from that attack right there. So that's how you can keep track of where things came from. Okay, and then from here, what did we do? This oxygen here is going to get protonated because... Wait, what? What's going on? Oh, wait, what? Oh, okay. I'm gonna do this step by step. I don't think this mechanism is gonna be tested because like she skipped a lot of steps here. So what basically happened was this OH here gets protonated. So let's ignore the other arrows. Let's ignore that arrow. Ignore this arrow. Oh, no. So this OH here grabs that proton. This bond between the OH goes onto the oxygen to create this intermediate right here. This will probably not be tested, but we have O minus there, and then we have OH2 plus here. Now once we have that good leaving group, we could go back down and then kick out that leaving group to get that product right there, which is this right here. And then this water creates that water right there. Yeah, don't worry about this mechanism. Okay, easiest way to make anhydrides, especially with asymmetric anhydride, is to use acyl halide. Yes, so this is the more reactive derivative. It's more reactive than this carboxylic acid. So that means that this is going to be the leaving group. And this right here is going to be the nucleophile. And we're going to substitute the chlorine with the nucleophile minus the hydrogen, right? The hydrogen is no longer going to be there. This entire structure here is this entire structure right there. Right? And then the hydrogen here is going to be in blue. And then the HCl comes from this hydrogen and that Cl leaving group right there. And this structure here is this structure right here, right? Where this is the new bond formed between them. Okay. Okay. So amides, if you have no heat, right? If you just have a neutral amine and a neutral carboxylic acid, an acid-base reaction is going to happen because this is the acidic proton. This is the basic molecule. This nitrogen here is just going to grab that proton and I give that oxygen a negative charge, which is this carboxylate ion here. And then we get this ammonium ion here. But if we have heat, like 200 degrees Celsius, we can force it to create an amide right here, where you could think of this as the leaving group, and then this as the nucleophile. And we could substitute the leaving group with the nucleophile to create this amide right here. In extreme conditions, heat, but it's not a good way to make amides. It's very messy, right? The better way is to use an acyl chloride, the most reactive derivative, right? The acyl halide, because the most reactive derivative, like we said earlier, does not require acid, does not require base. So it can happen in neutral conditions, like with a neutral amine right there, where this is the leaving group, this is the nucleophile, and we see that the nucleophile substituted the leaving group right there. Okay. And if we could do cyclic amide or lactam, where this is the electrophile, this is the nucleophile, and with heat conditions, 1, 2, 3, 4, 5, it's going to be this 1, 2, 3, 4, 5 molecule right there, intramolecular reaction, right? Where we just attack that, push that up there, and then keep going, nucleophilic aerosol substitution mechanism to get this lactam right here. Same process over here, but because we have ammonia, we're going to get this cyclic amide or imide. The mechanism is here, right? In neutral conditions, ammonia attacks the carbon-carbon, push the bonds to oxygen, get this tetrahedral intermediate. This O- gets protonated. This NH3 plus gets deprotonated. We get this neutral tetrahedral intermediate. We reform the carbonyl, kick out the OH. And then the OH minus comes back for vengeance because it's very angry, very unstable, and grabs that proton right there to deprotonate this positive charged oxygen to make it neutral. And then we have the water molecule right there, like that. Okay. Yep. This right here looks very bad because this is a bad leaving group, but it's able to happen because of the solvent around, like the other ammonia ions around, stabilizing that negative charge, right? So that's what this is talking about. And then that solvent can protonate the OH minus right away, right? But this is just one way to represent the mechanism. There's other ways, but this is how Lievens draws it. So I would stick with this. Okay, we could also do other reactions like reduction. We learned about this in 1A. We could reduce a carboxylic acid to a primary alcohol by just completely getting rid of the carbonyl using a strong reducing agent, lithium aluminum hydride, and acid workup, right? Don't worry about this mechanism. Just know that for vocab, you need at least 3 equivalents, right? 3 equivalents or excess of the lithium aluminum hydride to fully reduce the carboxylic acid to the primary alcohol. You would not be tested on this mechanism, but you can be tested on the concept that we need at least 3 equivalents of the lithium aluminum hydride. The next reaction is HVZ reaction, or the Helmholtz-Zielinski reaction, which would alpha brominate the carboxylic acid, right? So let's say this is the carbonyl carbon, this is the alpha carbon, this is the beta carbon, this is the gamma carbon, right? If you had more, it could be delta epsilon as well. If you use these reagents like Br2 with PBr3 catalyst or P catalyst, you're gonna put a bromine on the alpha carbon, right? So we see here we put a bromine on the alpha carbon right there, right? The mechanism is a note card thing, so I don't have to go over that. It's pretty tricky, but I would put that in your note card for sure. Now, once you have this alpha brominated carboxylic acid right here, we could do SN2 reactions, right? You could use a nucleophile like ammonia to attack that carbon, kick out the bromine to get this ammonium ion. You could use Cn minus to attack this carbon, kick out the bromine to get this cyanide ion. And then from here, you could use a reducing agent like H2PDC to reduce the CN to this primary amine, right? Where this C right here in blue is going to be that C right there, right? So don't forget about that C right there. Okay. The reason why like you didn't use lithium aluminum hydride and acid workup is because lithium aluminum hydride would have also reduced the carboxylic acid down, right? So if you used lithium aluminum hydride with acid workup, you would reduce both the carboxylic acid and the nitrile down, right? But if you just use H2PEC, this is a selective reducing agent, which is going to reduce the nitrile only to the primary amine. It would not reduce the carboxylic acid. If you used NaOH, the OH minus can substitute the bromine with the OH right there. And then you could oxidize this alpha alcohol with this oxidizing agent, H2CrO4, right? Which is Jones. If you see chromium and oxygens, this is Jones reagent. We have a secondary alcohol, which can be reduced to a ketone using Jones or PCC. You could have also used PCC to make that work from 118A. Okay. Yep. We talked about this. This is not carboxylic acid derivative. They do have the carbonyl, but there's no good leaving group, right? All of these carboxylic acid derivatives here have the carbonyl, and all the leaving groups here are good leaving groups that are able to leave, right? The aldehyde and ketones are not derivatives because they are terrible leaving groups, right? This is very unstable. This is also very unstable. So very bad leaving groups. They're not considered carboxylic acid derivatives. Nomenclature, I don't really want to go through that, but we could practice that next time if you guys want to. Then spectroscopy, I don't really want to go over that. And that's going to be it for this session. Oh, acid-base stuff. Acid-base stuff are pretty important. Let's go over that. Okay, so acid-base. The pKa represents acidity. The lower the pKa, the more acidic the molecule is. So we have a carboxylic acid here, we have an alcohol here, we have a phenol here, and we have a aldehyde or ketone here. The carboxylic acid has the lowest pKa, meaning that it's the most acidic, right? And the reason why is because when we deprotonate it to get this conjugate base, it's very stable through resonance, right? That negative charge is on an electronegative atom oxygen, and it can do resonance. But if you were to deprotonate the alcohol, you do get a negative charge on the oxygen, right? But that negative charge is not able to do resonance at all. There's no carbonyl or a double bond or triple bond to do resonance with. That's why it's not as acidic as this molecule here, right? Now the phenol here, right? You can deprotonate the alcohol to get a negative charge there, and you can do a lot of resonance with this benzene. And you might wonder, why is this pKa not lower than this pKa, even though it can do more resonance, right? This one can only do resonance one time, but this one can do resonance like more than one time, right? The reason why is because this is a benzene structure, which is aromatic, an aromatic structure, and we do not want to break the aromaticity of the molecule, right? That's why this is a higher pKa, because we want to maintain this aromatic structure right there. Okay, now the acidic proton for the ketone or aldehyde is the alpha hydrogen from 118B. When we deprotonate it, we get a negative charge on this alpha carbon, which can do resonance with the carbonyl here, the same as this right here. But this negative charge here is more stable because the negative charge is on the oxygen rather than a carbon, right? Now the aldehyde has a lower pKa because let's say these are the structures that we are comparing, and we get negative charges here and here. They both can do resonance with the carbonyl, right? But the aldehyde has a hydrogen that's not an EDG, so it would not repel that negative charge. Whereas the ketone has an EDG on the other side, donating electrons to the carbon-carbon, and that's gonna like repel electrons, right? Because negative charges repel each other. So that's why this is a less stable conjugate base, making the ketone's pKa higher, right? So that means the ketone is not as acidic as the aldehyde, right? Yeah, substituents affect pKa. The more electronegative atoms you have, the more acidic it is, right? Because if you were to have negative charges here when you deprotonate them, the most stable negative charge is going to be this one with the most electronegative atoms and the amount of them as well, right? Because those are going to pull on the negative charge, making it more stable, right? Making it more delocalized. Whereas this negative charge here has no EWG, right? No electronegative atom supporting that negative charge. Okay, the farther it is, the less stable it is. Because let's say we compare that negative charge with this negative charge. This negative charge here is more stable than this negative charge because the electronegative atom here is farther away, so it can't pull on the negative charge as much. Right. Dioic acids, first, second. Yeah, so the first, meaning that when you deprotonate one time, the pKa is very high, but the second time is this one right here. It's higher because we have like electrons going here now, and when we deprotonate this, these electrons will repel each other, making it less acidic. Right? Can be bases in very strong acids. Major. Yep, this is to talk about like protonating the carbonyl oxygen, doing resonance with that. This is the major resonance structure. This is the minor resonance structure because this carbon here does not have an octet rule. The number one factor for major versus minor resonance structure is the octet rule, right? Every single atom in this structure has the octet rule. This carbon here does not have the octet rule, so that's why that's minor. This is also major. They're basically the same thing, right? So they're both major. pKa forming ions. Okay. Yeah, so this is talk about the pKa of carboxylic acid derivatives. When we have a negative charge here, negative charge here, negative charge here, negative charge here, negative charge. Oh no, this is gonna be neutral. 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 Let's look at this top one first. The negative charge here is the most stable, right? Because it has a very electronegative atom supporting that negative charge. The negative charge here is very sad, very angry, because this nitrogen here is not able to pull on the negative charge as much. And also, this nitrogen here has a pair of electrons that is going to donate electrons to the carbonyl, which this negative charge does not like, right? Because negative charges repel each other. Whereas this chlorine here is not going to do resonance with that carbonyl because we said earlier that the p orbitals will not overlap. So because they're not doing resonance, this negative charge would not be repelled as much, right? So that's why this is the most happy, and everything else is in between. Same concept for this as well. Okay. Any questions on that for week 1? I'm gonna try to keep these weekly sessions an hour and a half, 90 minutes. Next time you guys can like send me questions, topics you guys want to go over the most, so then we can focus on that more, and then every other topic last after that.
Thank you.
Yep, of course. Okay. I'm gonna post these later tonight or tomorrow. Okay.
All right. Thank you.
Yep,
Have a
of
good
course.
night.
You too, Sharon.